All right, so continuing to look at circuits, we've got quite a few videos on this one, but I asked some questions that were a little bit different from some of the stuff in class or were a weird extension from class, so I wanted to have some that would actually supplement and help out. So, continuing to look, this one's actually a three-part question. So, assume electrical energy costs, so we're actually going to do a price here of the cost is $0.080 per kilowatt hour, so divided by 1 kilowatt hour. In short, they're saying assume that every kilowatt hour costs 8 cents. That's not actually a bad estimate based on what we saw in class, and I brought up our local electric company's rates, and we saw that that's actually fairly close. Right now we're actually a little bit higher, 9 to 10 cents per kilowatt hour, but this is still a very good value. All right? So, for all of our parts, we're going to assume that we have a price of this. Every kilowatt hour will be 8 cents. All right, and that appliances have a potential difference across them, delta V, of 110 volts. I kind of prefer to use 120 volts, but 110, 120 are actually both very good representative values for what we actually have in real life. Most regular appliances will have something pretty close to that. It turns out a lot of the appliances actually go off of AC, which we had talked about is the wall socket, and as a result, it's hard to get a good value for this exact number because it'll actually change. 110 or 120 is actually the best representative value that we usually quote. All right. A, it says calculate the cost of running a 75-watt stereo for 24 hours. All right, well, so in part A, they tell us that we've got a stereo, that the power is 75 watts, and they want us to find out how much it costs for 24 hours. T equals 24 hours. Well, in class, we found that the energy was equal to the power times the time, so we'd have 75 watts times 24 hours. Now, if we want the energy in joules, to get SI out, we need to put SI in. And while a watt is SI, hour is not. I apologize, out of habit, I always learned hour as HR, although it seems the standard might actually just be H. So bear with me on that. All right, well, I multiply these out, and I'm going to find that the power that I get is 75 times 24. We end up with an energy of 1,800 watts times hours, which would be called watt hours. Now, we're not charged for watt hours, we're charged for kilowatt hours. And remember, kilo means that we're going to have a factor of 1,000. So our energy here, I can divide this by 1,000 and I get 1.8 kilowatt hours. To find my price, that's going to be equal to my energy times the cost of it, which we said was, let me fill this in. My price is going to be, our energy was 1.8 kilowatt hours, remember, unit of energy, times it costs $0.080, 8 cents, per 1 kilowatt hour. The kilowatt hours cancel out, and I'm left with units of dollars. So I take 1.8 times 0.08, and I find that my price comes up to $0.144, or about 14 cents. Let's see what they've got programmed in here. The correct answer, they want this in dollars. This is the correct answer. Go ahead and put a couple of extra significant digits on there. Even though you're not going to pay 4/10 of a penny, remember the system looks for if you're close enough to it, so don't ignore kind of the significant figures. This is the number that you'd actually put in. The real life value would be 14 cents. They might round that up to 15 cents, but it depends on how they're collecting your bill. So, all right. That's part one. Part two. Okay. Yes, there we go. So, B, it says calculate the cost of running an electric oven that draws 26 amp of current for 24 hours. So they're going to make this a little bit more difficult. We've got the next question. But remember, we're still using the same things that we had before. So our current, they tell us for this oven, is 26.0 amp. They told us at the beginning that the potential difference, the voltage, could be assumed to be 110 volts for all of our appliances. We didn't need it for the last one because they gave us the power outright. This is also why, back when we talked about electrostatics, that potentials were so useful to deal with, because now it's something that is completely independent of your object. Doesn't matter if you're plugging in a washing machine or a night light, they both take this same potential. Now, the energy that they take, the power that they take, which is what we're looking at here, is going to be related to how much current they draw, as well as the potential difference. And so this remains constant for all of the objects, but this will actually change based on the design of the object. So as we go through when we're studying advanced circuits, that's something to keep in mind. This is why we deal with potential differences, because they're independent of the objects that we connect them to, at least in ideal settings, what we're actually looking at. And in real life, the value won't change very much if it does at all. All right, they want to know how much it'll cost to run this for, dear Lord, 24 hours? Keeping an oven on for 24 hours is not going to be cheap. Let's see. All right, so if we want to find the price, here's where we do some of the stuff that we did in class. First step is going to be to find out how much power we're actually dissipating or consuming or moving somewhere else, basically. So in this case, we find that our power is going to be equal to 26.0 amp, a very large amount of current, times delta V, which is 110 volts. I apologize, I'm not using the colors on this, but this one is red, this one is blue, in keeping with my usual color notations. I multiply these out, and we find that the power, 26 times 110, is, well, this is noticeably different from the stereo. 2,860 watts. Okay? We could also convert this over now into 2.86 kilowatts, dividing by 1,000. And if we want to find the actual energy that we consume, that's going to be the power times the time, which will be 2.86 kilowatts times, they told us we leave this on for 24 hours. So, multiplying this out, I find that the energy that we consume is going to be, multiply these out, you get 68.64 kilowatt times hour, kilowatt hours. That's what that unit is. And if we want to find our price, that's going to be equal to our energy, which is 68.64, that's what we're charged for, in kilowatt hours times, here it is again, 8 cents per 1 kilowatt hour. We find that the kilowatt hours cancel out. I multiply this by 8 cents. And we find that the price comes up to $5.49 and 12/100ths of a cent. So basically $5.49. But again, with the online system, go ahead and put in a couple of extra significant digits just so it's certain that you got the right answer. $5. Pardon me. And 49 cents. This is, in fact, the exact answer that they've got listed there. So this is how you go through and solve that one. Like I said, this is a 3-part question, so let's take a look at the last part of this question. Calculate the cost of running a television with a resistance, of 30 ohm for 24 hours. Here's where one of the things that I mentioned in class is going to come in handy. So we've got a TV. And either that or an alien. We've got a TV, and we've been told that it has a resistance, that's interesting, of 30.0 ohms, at least for my numbers. We're going to be running it for 24 hours. We don't know how much current it draws, but we do know from the very beginning that they told us that we could assume that all the appliances have a potential difference of 110 volts. here's where we use one of the other things that I gave you. I told you that power, while it does equal I delta V, there were also other things that it equaled. It also equals I squared R, and it also equals delta V squared over R. Now you can go through and you could apply Ohm's law, and you could go through and you could try and find the current with the resistance and the potential difference, and then you could find with the current, you could go through and do this. But remembering that this equation exists will save you a step. Okay, well my power of this object is going to be delta V, which is going to be 110 volts, quantity squared divided by my resistance, which is 30 ohm. Well, let's see what we end up with. 110 squared divided by 30. I end up with a power of 403.33333333, whatever. I put SI in, volts and ohms, so I will get SI out, and I'll end up with watts. Great. So this is my power. If I want to find the energy, that's going to be equal to my power times my time, which will be this value, 403.3 repeating, if you prefer. Normally we don't keep that many, but again, we've run into issues with rounding errors with the online system, so for this, I'm going to leave that for now. We leave it on for 24 hours, not necessarily a good thing to do. It's important to try and conserve power whenever you can. So I'm going to multiply this by 24, and if you keep 403.33333333, all those extra ones, when you multiply these out, you find that the energy comes up to 9,680 watt hours, which I could divide by 1,000, and that would give me 9.680 kilowatt hours. We get to our last step, that the price is equal to 9.68 kilowatt hours times $0.08 8 for 1 kilowatt hour. Kilowatt hours cancel out. We multiply these out. So divided by 1,000 to put it in kilowatts times 0.08. We end up with, if I've done this correctly, hopefully I've not made an error because this seems a little small, but 0.7744 to leave this particular television on for 24 hours, according to this, comes up to about 77 cents. Let me see if I've got that right. Yep, 77 cents is what they've got here. I don't know how realistic that actually is. I'd have to take a closer look on it. One final thing that I'll bring up is this. On the very first one, you don't have to do this, but it doesn't hurt to think about it. If we've got the stereo plugged in to the wall potential difference of 110 volts, and the power is 75 watts, we could actually find that 75 watts equals 110 volts times the current. The actual current that draws, I can actually solve for that, one of the other things that we didn't specifically look for outright, but 75 watts divided by 110, and we end up with the stereo pulls 0.682 amp, at least the three significant figures. You're not asked for that, but while we're playing around with some of this, I thought I'd point that out. You could also use, assuming that this is a DC circuit, most stereos I assume would be, you could find with the potential difference and the current, in fact, let's take a look at that. 110 divided by that value, we find that it has a resistance of about 161.3 ohms. There's a bunch of other things that you could find that were not necessarily asked here, but might be asked in the future. This one's kind of a long problem, or at least I would say that, except it's 3 problems all in one. And it applies some of the stuff that we did A in class and B with those sample problems as well.